Welcome to session 3 of Outsmarting contracts. We've been through a lot. We've traveled already a long way through some of the history of Ethereum, through looking at what it means to use MetaMask, what an injected Web3 provider is, how to program from your browser without any kind of fancy code editor or any other software, how to interact with contracts directly from your web console. We've spoken a little bit about JavaScript. And yes, well, last week, feels like yesterday, but it's time. Last week, we took a look at writing our own smart contract for the first time in Remix, which is the integrated development environment provided by the Ethereum Foundation. So my intention last week was to also do the telephone tutorial from the Ethernauts setup, which we didn't get around to because, as per usual, my computer decided halfway through that it had had enough of me rambling on and cut me off, which is really wonderful. I'm enormously grateful for these constant reminders. So we'll start with the telephone, just to sort of remind ourselves what it means to write a smart contract and to look again at this pattern of writing an interface and then using, sort of another contract to attack the smart contract that we want to gain control over. And to remind you again that this is like a technical expression of what we really mean by complementary opposites, right? That's it's only by looking at and understanding how we can attack our code and our smart contracts that we can really develop an intuition and understand what it means to write safe, secure, robust, and resilient code. You can't really understand the language of defense or this notion of defender's advantage unless you think like an adversary, right? The way that I like speaking about this is to say that, in order to imagine a different kind of economics, you need to dream like an idealist, but you need to think like an adversary. Right? That these two things go together. Just idealists, no good. We end up in some kind of imbalanced utopia which holds its own seeds of destruction. But if you're capable of holding these two complements together, the idealistic one and the adversary, you can potentially write more secure and robust code that then allows for interesting interactions and relationships to form of their own accord above it. So without too much further ado, because there's been a lot of ado in the previous guild sessions, much ado about nothing, in fact, if you're that way inclined, then we will get immediately into the first Ethernauts tutorial, which we began with coin flip last time, and we're going to take a look at telephone this time. This is a fairly straightforward example, but it's really, really useful to begin here because it's just going to remind us about like the pattern, the very basic pattern that we'll be using on a number of different occasions in this guild to attack other smart contracts, and which is used and has been used to great effect by many different hackers, both black and white hats in the ecosystem over the years. So make sure that you have Ethernauts open and your MetaMask open and connected to Rinkeby with the accounts that has some Rinkeby Ethernets. Let me know if you need some Rinkeby ETH. Scream now or forever hold your peace. Wonderful. And make sure that you have Remix open as well. We'll be just reminding ourselves about what we did last week and then diving into telephone. So in Remix, you'll remember that we have a number of different functions along the left-hand side of the screen here. The first is our file directory. It's where we keep all of our contracts It's where we keep the scripts that we use to deploy them. We were using the Ethers scripts. We just had to change the name of the contracts that we wanted to deploy. It's where we write our tests, particularly Solidity tests, which are wonderful and not very often used. And it's where various different plugins that are available on the home screen come from. And I'm running through the LearnEth one myself at the moment, and we'll talk a little bit about that today when we get to storage. So this is where we were last week, and we had written our first smart contract, deployed it onto Rinkeby, and attacked CoinFlip and got it right 10 times consecutively, which was the point of that tutorial. And just to kind of remind you what this was about, we sort of declared the license that we're going to use for this contract. It's not completely necessary, but it does really help to have this license identifier. And we sort of, I mentioned very, very briefly that I really like the MIT or the GPL, the GNU GPL licenses, which are both share-alike licenses. So they mean you're free to use this software, copy it, and distribute it as you like, but you have to use the same share-alike license. You can't take this open source code and lock it down and then sell it in some kind of corporate context. You have to share it as it has been shared with you. It's a wonderful license. Then
Andy, you're not sharing your screen.
Oh man. Thank you, Guillermo. Hilarious. There we go. That should be better.
It was a little hard to follow you.
Wonderful. Please excuse me. I got ahead of myself already. It generally takes at least 20 minutes for me to wind up to be ahead of myself, but today we're straight into it. So this is where we were in Remix, and as I was saying, you've got all of these different functions along the left-hand side of your screen: the file directory, the compiler, deploy onto various different networks from this Ethereum logo with an arrow, and then the debugger and various other things that you can add by sort of getting plugins from the home screen. And this is where we were in terms of writing our smart contract to attack the CoinFlip tutorial last week. We had written the contract in our contracts folder, and we'd used the deploy ethers script by just changing the name of the contract there to attack CoinFlip, the name of our contract. We deployed it onto Rinkeby, and we'd consecutively guessed the correct answer 10 times in a row. The reason that we were able to do that is because of these global variables, right? Block number and block hash are kind of available to everybody. And so we could calculate what the CoinFlip contract was going to calculate in the same block, figure out what the result of that calculation was going to be, submit the right answer, and gain all of the winnings from our supposedly pseudo-random CoinFlip, precisely because of the nature of the environments within which we're working. And the way that we did that was by sort of declaring the license, by saying what version of the Solidity compiler we're going to use, then creating an interface which declares only the function that we're interested in, sort of the functions that we're interested in calling in the contract that we're creating an interface to, instantiating that interface at a particular address, which was the instance address that we had created in Ethernauts, and then writing one function which had exactly the same logic as what we saw in CoinFlip, calculated what CoinFlip would calculate, and then guarantees that we would submit the right answer to it every single time by instantiating the CoinFlip contract and calling flip on it, which we've defined up there. So this is quite a common pattern in terms of contractual interactions on Ethereum, and it's exactly the same pattern that we're going to be using for the next tutorial, which is telephone. And if you take a look at your telephone tutorial in Ethernauts, you'll see that it's very, very simple. All we have to do is claim ownership of the contract below to complete this level. And if we look at the contract, it's also extraordinarily simple. It has the license and the compiler version. It declares this contract telephone. it tells us that there's one variable in storage, which is this owner variable. It tells us that as the contract is constructed, the person who sends the message that instantiates this contract is set to the owner. And then there's one function, which is change owner. And what this is saying is that if the transaction origin is not equal to the message sender, then set the owner to whatever address is passed in this function. Right? So we have to figure out a way of sending a transaction to change owner here, where the origin of the transaction is different from the message sender. And of course, we can't do that from our console, right? Because when we send a transaction directly from our console, then where the transaction originates and who is sending the message is one and the same thing, which is our player account. So again, we're going to have to write our own contract. And in that case, when we can write our own contract that sits between us and this telephone contract that we actually want to call, then the transaction origin will be our account, our player address, but it will get sent to our contract. And then our contract is the one who will be calling telephone. And so our contract will be message.sender, right? And in that case, the transaction origin, our player account, will be different from the message.sender, which is our contract. So this one it's actually much more simple than the coin flip one, because we don't have to copy a whole bunch of different logic and think about making sure our contract is going to sort of like calculate exactly the same thing. We just have to understand this thing about like more and different kinds of global variables that are available in Ethereum. And we have to understand a little bit about context, which is something that we're going to look at quite a lot today. And if I can, here are, just to remind you, the kind of globally available variables. We were looking at block.number and the block hash function in our coin flip one, which were globally available and therefore the same for every single contract at every single block in the network. And today, this first tutorial is getting us to look at tx.origin and message.sender, which is something that we've seen a little bit of, but tx.origin is what we're going to start looking at today. And we'll extend our understanding of this by looking at the next tutorial, which will be delegation, because that has to do with the origin of transactions and this notion of context, right? Context being like all of the information that is passed along with your transaction. Message.sender, message.data, message.value, tx.origin, tx.gas price. All of these things are the context in which any transaction takes place. So, as I say, if we manage to stick our own contract between us calling it and the telephone, which is specifying that the origin needs to be different from the sender, then we should be good, right? So if I go across to Remix, in the same way that we did last week, we can create a new contract. We'll call this one attack telephone.sol, just as we did with attack coin flip. We can, and let me just make sure that you can see what I'm doing here. We can just grab those two, the license identifier and the declaration of the compiler version. And then we're going to follow exactly the same pattern that we did last week, which is the first thing that we're going to do is write an interface. And the interfaces always begin by convention with I, and then the name of the contract. So in this case, I telephone. And we're interested in only one function, right, which is the change owner, function in our telephone contract. And if we take that and just declare it in our interface, as Guillermo so kindly pointed out last week, we need the external keyword, not the public keyword. And in fact, yeah, Guillermo, and for others, if you're interested in this, the difference between external and public is kind of an interesting one, and it touches on a lot of what we're going to talk about today, which is storage. So public functions, they put data into memory, right? Because they're expected to be called from internal functions as well, and internal functions are expecting that data to be in memory, whereas external functions are only concerned with call data, right? I will explain a lot more about like storage, memory, call data, and the stack when we talk a little bit more about like delegation and some of these other, the vaults we're also going to do today. But this difference between external and public is a subtle one, and it has to do with the difference between memory, which is what's associated with public functions that necessarily have their information like in memory because they need to be accessible to other internal functions in the contract, and call data, which is really just the function parameters, and is often used to make execution even cheaper in terms of gas costs. So this is something that we'll like cover a few times in today's tutorial because it's subtle and really interesting, to be honest, because it points at the actual structure and architecture of the EVM itself, which we'll also discuss a little bit. But anyway, we have the external keyword there. And then we're going to write our contracts, right? Which we're going to call attack telephone. And in exactly the same way that we were creating, specifying where our instance is and then pointing our interface at it, we're going to do exactly the same thing here. So let's first just go and make sure that we have our own instance of telephone, which means that we'll need to get a new instance here. I can confirm that transaction. And play light, jazzy, elevator music while we wait for our transaction to be mined, which is there. And if we come back, we'll have our address, which we'll call telephone address. And you can set this equal to your own instance address. Then we'll declare our iTelephone type, and we'll call it telephone contracts, just like we did last time, and have iTelephone at our telephone address. So that sets up the interface exactly how we need it to be and points it at the correct instance on, in this case, Rinkeby, but whatever network you're working on, this pattern would work. And then we want to write a simple function which is going to call change owner and make sure that the context is different between transaction origin and message sender. So because we're feeling a little bit more black hat today, maybe let's call our function pawn. We don't need any, you can see there's no parameters required for this necessarily. All we need to do is make sure that the address that we want to become the owner is sent to our interface address. So we just need to make sure that this is a public function. And in here, all we're kind of concerned with doing is looking at the telephone contracts, calling the change owner address, and here we have to pass in some address. So we want it to become our owner. And I mean, this is just your player address, right? Which you can copy directly out of MetaMask if you like, or the alternative way of doing that is just to remind you that all of these things are also accessible happily through the console on Ethernauts. You can just check that it is the same thing, which it definitely is. And that's all we need, right? We've created the interface that through which we're going to speak to our instance. We've told our contracts exactly where our instance is. And we've written the one function that we're going to need to call the function on the contract that we're interested in and pass the correct owner to it so that we can claim ownership. This contract here, attack telephone, is going to be the message.sender, and the transaction.origin will have come from us because we're the one who's calling, we're the one who's sending the transaction in the first place. So if you go back to your deploy ether scripts and just make sure that this is called attack telephone now. Wonderful. You can come to the next tab down in your IDE, which is this compiler tab, and make sure we've got attack telephone selected in our screen. We're going to use the correct compiler version. Okay, doesn't really matter. And hopefully it will compile. Let's see. Had a few issues with this last week, but hopefully this time I'll have got it right. It can take a little while. You can also, I mean, like I've got 0.6.0 as my pragma there, but you could use 0.8.0. It's probably better. I just copied this in haste from CoinFlip last week. And so it's fetching a new compiler version, which is why it's taking a little moment to make up its mind about compilation. While that happens, we can answer any questions.
While it is still compiling, I have a question. Please, can you throw more light why you choose to use interface? I'm not clear about that. Why you decided to go with implementing it with interface?
For me, so you're right that it is a choice. Right? There are other ways of instantiating like a contract that you want to speak to from within your own contract. For me, it just has to do with a certain kind of like logical way of thinking. Modularity is something that I value enormously, and being clear about what is doing what and where it is happening, like it's something that just appeals to me in terms of the way that I think, which is not right or wrong, right? There are many different ways to approach these things. It's just that like here it, you know, like it's like, okay, you could probably just instantiate this within your own contract and off you go. And it makes no real difference, right? Because it's very, very simple what we're doing here. But when you're writing like production level code and you want to do like a whole bunch of different things and you're interacting with 5 or 6 different libraries at different points in your code to achieve different stuff, then like having it split into interfaces and being very clear about which interface is being called when and what function is being instantiated through that interface, it just helps me from like a logic and readability perspective. As far as I'm aware, like this is best practice. As I say, there's like a lot of other ways perhaps of doing these things. And I hope to like have made clear through the course of these guilds that like this is just one way of doing it, and it's not necessarily the right way. There is so many, like the possibility space with these tools and technologies is literally infinite. You know, that like we're also going to look at that today. Just in one contract storage, you have a near infinite amount of storage capacity potentially that's limited by things like the heat death of the universe and the amounts of money that exists. But there is just infinity on kind of any side, wherever you look, whether it's in the language and how you write these things, whether it's in the actual architecture of the EVM, whether it's in the storage available to each contract, whether it's in the number of addresses that could possibly be instantiated. All of these things are nearly infinite, or might as well be, as far as like we are concerned from our limited perspective in space and time. So given all of that, I really value the separation of concerns because it just makes it easier to reason about for me, and it makes it easier to read for others. So yeah, you don't have to use an interface. If that way of thinking about things and splitting up your logic doesn't make sense, then by all means, do it another way. But yeah, this is just kind of my sense of things. So we have, and thank you for that question. I really appreciate it. A, because it's really fascinating, and B, because it's allowed us to compile in time. You see a nice little green tick next to my compilation there, all is well. And if you remember from last time, we want to use our injected Web3 provider, which connects to Rinkeby from MetaMask. And it is indeed the account that I'm interested, the 0x5F3, which is what's going on there. And once I'm happy with all of that, I can deploy it onto Rinkeby, which is our second smart contract ever onto an Ethereum-like network. Very, very exciting stuff. We can play some more delightful jazz elevated music. By the way, I highly recommend the Washington Keys video that Amarnath puts in the Jam music channel in Slack. It's unbelievable. I love that. So if you're looking for some music while we wait for these transactions and stuff, that's a good place to go to. But you can see that my contract has indeed been deployed. Very exciting. All of the functions available on it will be here under your deployed contracts in your this left-hand sidebar. And the only function that we've written is the spawn function, and it doesn't require any parameters or anything. All we need to do is call it, which is very exciting because it is going to be changing states. We need to submit a transaction. The reason that it's going to be changing state is that owner, that address is declared in storage. That's gone through immediately. So when we change storage in a contract, we're changing the state of the network as a whole. Now that my transaction has gone through, I can go back to the Ethernaut tab. And if I await the contract owner like we've been doing, then I can see, it's me. Yay, it's me. Wonderful. That's really exciting. It seems like we might be able to submit our instance, have it get checked by the main Ethernaut contracts, play some more delicious jazz music, or speak about logical interfaces and separation of concerns, until we get this rainbow effect through our console. It's still like one of the coolest things in the world. Huge props to the Ethernaut team. And as per usual, you will see, although this is like a fairly simplistic setup for a tutorial, you can see some information about like when this kind of thing has resulted in a hack. And you'll sort of see that this is mostly to do with phishing style attacks and using tx.origin to determine whose tokens to transfer, which is not a very good way of doing things. So when you use these global variables, whether it's block hash and block number, like we saw last week, or tx.origin and message.sender, just be very, very careful about context. Context is everything in life as well as Solidity. These two things not being all that different. And it's really important to be deeply aware of what information is with your text, with your transaction, which is what context means. The Latin prefix con means with. It's the information which goes along with any transaction that you're sending. So there are there's a little bit of fun kind of things to look into about phishing styles attacks and these sorts of things, which you can do now that we have conquered level 4, which is telephone. So you should have text next to fallback, fallout, coin flip, telephone, and token, because we did token and overflows at the beginning of last week. I messed up a little bit, and when I was testing my ability to do delegation, I did it from the wrong account, so it has a tick, but that's what we're going to do now. and the intention of delegation is to once again become the owner of your instance address. You kind of have got some insight into where this went really badly wrong, which was the parity wallet hack. And we're going to talk a lot about these different. This is a very kind of it's a very simple hack. This one, we're not even going to have to write our own smart contracts, but it has enormous complexity under the hood, which I'm honestly not even sure I'm fully qualified to explain, but I am going to give it my best shot. And so if we sort of read through the contracts ourselves, as we've been doing, we have our usual license identifier and compiler declarations. And then we have two contracts together here, right? Delegate and delegation. The delegate contract declares an owner. It sets that owner in its constructor, which is when it's deployed, it's passed some address parameter, which is set at the owner as the owner. And then it has one function called pawn, which is the one that sets the owner to whoever sends it this message, right? So that's fairly straightforward. And then we have this delegation contract, which also declares its owner variable first up. This is important because when you have this kind of pattern and when you're using delegate call, the structure of your storage in your contract has to be the same. So you have to declare, it's really important that this line is declared first as it is declared there, because it's stored in the same slot. And if these words are unfamiliar, don't worry, I'll explain each one of them as we go along. But when you're doing delegation, which is often used in libraries and the kinds of contracts that are either those which contain logic which is used by many different contracts in your contractual ecosystem, or often you find this kind of pattern in sort of proxy contracts and upgradable situations. It's really important that your storage stays the same, and this gets into some very subtle aspects of the EVM and how Solidity works, which we'll be looking at. And then in our delegation contracts, we set up a type delegate, which we call delegate. And this delegation contract is constructed also with an address that is passed in, which is what is set as our delegate of type capital D delegate. I know it can be a little bit confusing with these different types and variables named very similarly, but we're just at the level of Solidity telling the delegation contract where its delegate is. It's in the same way that we were looking here. We sort of telling our attack telephone contract where it's where the telephone contract is that we want to attack, and telling it that it's of this type interface. It's the same thing basically that you see going on here. And we set the owner of the delegation contract also to whoever sends the message that deploys this contract. Then there are no functions in the delegation contract. There's just this fallback. And in our fallback, we have this low-level call, this delegate call thing. Right? Delegate calls return booleans, and what you're looking at here is like it's declaring a boolean of results, and then this comma is just syntax for and whatever comes after it. So sometimes if you see like commas in Solidity, it's similar to the JavaScript syntax that you might sometimes see, that like if it's like boolean and then 3 commas, it's like the result and then like the thing that comes 3 after the results. In this case, 1 comma is just like whatever comes after the results. If there's result and anything that happens as a result of this delegate call, bundle it all up together, and I'll get to that in a moment. What we're saying is go and look at the delegate contract and delegate call any data that is passed in this message to that contract, right? So take whatever the message.data of a transaction that is sent to our delegation contracts, go and delegate call it to our delegate contract, and return whatever the result is, right? Which is as terrifying as it sounds. Now, the reason that we're doing this immediately after the telephone contract is because the two are tied together in quite an important way, right? You'll remember that the telephone contract is all about the difference between transaction.origin and message.sender. And sometimes it's really, really useful to be able to pass that context along and keep it the same. So in the previous example, our transaction.origin was our player account, and then we called our contract, which then called telephone, and it became the message.sender, right? But sometimes we will want a situation where we can send a transaction to our contract, and then it can call some other contract, but pass the same context along, so that message.sender and tx.origin are still the same. And that is the reason for the existence of this delegate call low-level function in Solidity. Right? It passes the context along. So if instead of kind of calling this contract normally, like we just did here, if we had delegate called it, then we would not have become the owner, because tx.origin and message.sender would have been the same. Right? So this delegate call is all about like passing the context along and keeping it the same, no matter how many contracts are called along the chain. And this results in something really interesting, right? Because what is actually going on here is that you can change the delegation storage, in this case, the owner address, from within the context of delegates. Right? This is like it's a subtle thing to try and understand, but there's a wonderful diagram here which can help us, right? That like here, this is our delegation contract, contract A, and this is our delegate contract, contract B. They each have their storage associated with them, storage for A and storage for B. We declare some variable in our first slot. And again, I'm going to explain slots soon, I promise. And if we have some delegate call function in our delegation contracts, which we do here, right? There it is. Then this calls the function that we're targeting in delegates, and it can actually mutate the storage in A, right? If you sort of like follow the logic through here, what's going on is that like we've declared bar in contract B, and so at slot 0, they have this pointer in memory to bar. But now from A, we've delegated called this function called set to 5, where in contract B, it's exactly what it does. It sets bar to 5. In our particular example, it's not foo and bar, it's owner and owner. And the set to 5 function is pawn, right? We want to call this pawn function, and it changes the owner to the message.sender. The same thing is going on here, just in more generalized terms, with foo and bar, who are much like Alice and Bob, common culprits in computer science. So now, like in contract B, you have at slot 0 this pointer to bar, but like what it actually goes and does is, because of the nature of delegate call, it sets foo equal to 5, right? Because if you take a look here, contract A, which is delegation, invokes the function. In this case, we're going to invoke pawn, and it overrides contract B storage with the storage of the calling contract. So that's what delegate call actually does at a low level, is it takes storage of delegation. It says, we're overriding whatever is in delegates, and we're going to like change it from within the context of delegates, but it's going to be applicable to delegation. So if you like read through here, you'll see that when contract A makes a delegate call to contract B, it allows contract B to freely mutate its storage A, but bar remains out of scope and is untouched. So this is like, I know this is like a little bit deeper down the computer science rabbit hole, but it's a really, really fascinating pointer to the underlying storage and architecture of the EVM, right? Because these slots are really wonderful things to try and understand, because they point at both the beauty and the impossibility of some of the stuff at the lower level of Ethereum and networks like it, right? Because how many slots can you have associated with a given contract? The answer to this is that you can, it's 2 to the 256 keys available in slots, and each key can store 32 bytes, right? Or 256 bits. So it's about 2 to the 261 bytes that can be stored in contractual memory, which is significantly bigger than the number of atoms in the universe. There are some wonderful, there are some wonderful Solidity Stack Exchange, Ethereum Stack Exchange questions about this, which is this one that I'm actually kind of interested in. Like, is there a theoretical sort of limits to the amount of data that a contract can store? I will drop this in our chats because it's kind of fascinating.
Delegation also allows to update contracts that are on the chain already, right? So
yes, it does. Yeah, and this was the cause of the parity wallet hack, right? Is that it delegate called some of its libraries in an unsafe way, and that meant that somebody could instantiate a self-destruct on it, and so they didn't hack the parity wallets. They didn't get the funds which were in it, which were significant. You know, I mean, it's well over $100 million. These, and more than that, I think, these days with the ETH price. At the time, it was like $100 million. These days are so much more. They just killed it. They self-destructed it, which is something that we're going to look at today, because it is possible to do these things if you don't implement delegate call in a safe way, right? Like this particular sentence, wherever it is, right, it should really terrify you. I mean, it's really also like, it's incredibly powerful to be able to use this particular kind of pattern in your contracts, because it does allow for really interesting proxy upgradable things, and again, like the sort of separation of logic in a easy and readable way. But this thing that like it freely mutates its storage A, right? Like that's terrifying, and that's what happened to the parity wallets, because like it was deployed on Kit chain. It used this delegate call functionality because like Gav Wood actually kind of wrote a lot of Ethereum, and he was the lead at parity at the time, and they implemented delegate call badly in their multi-sig wallets. It used these libraries that they delegate called to. Somebody managed to slip a self-destruct in there, and that ether is now forever inaccessible. There were so many things that happened around that. They wanted to fork the chain again, but it was much later on after the DAO hack. It never happened. I think it was EIP 999. I think that was the number of it. But if you're interested in this kind of stuff, there is a wonderful thing, which I'm going to come back to when I talk a little bit about some of the other sort of subtleties around storage on Ethereum, which we'll come back to in the nuts in a moment or two. It's just that I really wanted to touch on this notion of slots and how storage can be accessed and changed from different contexts using different contracts. And this is the reason for like delegate call, beyond just like passing context, so that tx.origin and message.sender stayed the same. There is this much deeper reason for having delegate call as a low-level function, which has to do with the ability to change storage from different places in different contexts, which can be incredibly powerful and therefore also incredibly dangerous. So what we're going to want to do, right, is...
I have a quick question, Andy, if you don't mind.
Absolutely.
I know that there's a difference between the way values are passed depending on the type of variable. But I'm not actually exactly sure, because I know that some variables are just copied and some are passed by reference. So so basically, like, does the choice of variable kind of like determine what's happening?
Yes, you're really, that's a wonderful question. I mean, you're really testing my knowledge there, because these have to do with, again, like subtle aspects of how memory and the stack works. But basically, any array or mapping is put in memory when you're working with it. That can be overridden by using like memory or storage keywords in your contract. And uints, strings, and bytes also like can be sort of stacked together without necessarily like that same like full reference in memory. They can exist only sort of in cold data. It's got to do, you know, like the yellow paper and the way that the EVM is structured means that you know, like mappings and arrays have their own. They always occupy one full slot, whereas like uint 8s, for instance, or strings, these other things need not do the same thing. And so because of that architectural decision way down in the yellow paper, then sometimes you can get away with in particular like uint strings and bytes, or even enums and bools as being like just in cold data and without having references to memory. But generally speaking, mappings, complex mappings and arrays are always sort of directly into memory.
Okay, great, thank you.
It's a pleasure. There's a really wonderful, if you go to our resources and the smart contract tools and practices, in the less reading, more watching videos, this will it scale. I don't want to open it because like opening YouTube in my browser while I'm also recording Zoom and running Remix last time was a total disaster. But if you watch, this is a playlist, and I think that it's video number 8, which has to do with like debugging Solidity. And in there, this amazing man speaks about the difference between the stack, memory, and storage. And you'll get like a lot of insights about what is actually happening with stack variables, how they're allocated, how the code jumps to certain different locations depending on how it's called and where it fails. It will also give you like great insights into this debugging tab in Remix. So like I highly recommend this. Will it scale? The other ones were recommended by like other people in kernel, and they're good enough, I guess. This will it scale is really wonderful. It's a little bit old these days, but like really, really good. And this particular thing about like, hang on, how does cold data, stack, memory, and storage actually work, and what is going on when I pass in different kinds of arguments? Yeah, this is probably the best that I know of, Sylvia.
Amazing, thank you.
Sure. Okay, so what we're going to try and do here conceptually, right, is we want to send a transaction to delegation, which will trigger the fallback, right? So we just have to send transaction without naming it anything, because like any transaction to a contract that doesn't specify what function it's calling or calls a function that doesn't exist triggers the fallback. This transaction that we're going to craft to delegation needs to have some kind of message data associated with it that will trigger our pawn function in delegates, which will change the owner of delegation, right? Because delegate call allows for delegates to freely mutate its storage, right? So when we call pawn here via the delegate call, it's actually going to change the owner in slot 0 of delegation. This is a wonderfully convoluted series of events that's going to take place with the result of just one transaction, but it's really revealing about the, shall we call it, interbeing of contracts on Ethereum, you know, with due respect to Shipman Han and the beautiful ideas that really underpin what he's talking about there. But like delegate call is kind of like the technical implementation of something like that, which is interesting to me. The way that we're going to do that is by getting a new instance, as per usual. And as I say, this one doesn't require writing our own contracts. This one we can just do directly from our JavaScript console with a little bit of understanding about how the EVM knows which function to call. And the way that it does that is any function declared in a contract has a name, and then it has some parameters associated with it. Solidity knows, it encodes the function signature as the first 4 bytes of the kekak 256 hash of the function name plus its parameters. I know that's a lot of big words all at once, but basically what we do is we take the function name and whatever parameters are associated with it, we hash that using the kekak 256 function, which is just a particular kind of hash. And then the first 4 bytes of that hash are how we identify the function. So it's 0x, blah, blah, blah. The first 4 bytes. This is useful in any number of places if you ever do write your own applications or this kind of stuff, but it's just like it's just a feature of how the EVM is set up that you kind of have to know about. It's by convention, it's standardized in the yellow paper, and it's just, as I say, the first 4 bytes of the kekak 256 hash of the function is how we know what it is.
That's so interesting. Is that why you can like have like functions with the same names as long as the parameters are different?
Yes, exactly.
Oh, that's so interesting. I was always wondering why like the language allows you, to have to name functions the same.
Yes, yeah, it's exactly that, because it's not actually a collision, especially if you have different parameters. Yeah, wonderful. Incredible. So as I say, we're just going to send a transaction to our delegation instance, which is what we actually have here. And we're going to pass along a particular piece of data, which is going to call this pawn function. And that piece of data needs to be the first 4 bytes of the kekak 256 hash of the function. The way that we're going to do that is by using the await keyword as per usual, and we're going to use the same send transaction thing that we did in our fallout. Was it fallback? Fallback was where we were using the send transaction functionality. Send transaction is a function, right? And we're going to pass along some JSON, which we always declare by using curly brackets. Let me just make that bigger so you can see what I'm doing. And the data that we're going to associate with this message is going to have it's going to come from someone, right? Which is the person that I want to make the owner is my player address, right? So I can grab that. It's got to come from me. Let me maybe just use double quotes. I don't think that makes a difference. We're going to have to send it to something, right? Always from and to in these send transactions. And the place where I want to send it to is my instance, right? So I want to, so this is a transaction that's coming from my player to my instance. And I want to pass some data along with it, right? This message.data, which is going to get executed in the delegate call that we're interested in. And the question is, okay, like what data? What data can we use, right? How do we get the first 4 bytes of the kekak 256 hash of the function? And happily, our Web3 library can help us with that. So Web3 has this part of it called ETH. So if we go web3.eth, ETH has part of it which is called the ABI, right? Which is wonderful, our application binary interface, which is what's speaking to all of the different functions of our contract that we've spoken of a little bit. And the ABI comes with this hell of a convenience thing associated with it, which is encode the function signature, right? That's the one that we're interested in. And this is a little JavaScript method in our Web3 ETH library that just allows us to do exactly, it takes the kegak256 hash of the function signature, puts the first byte, four bytes, and does what we need, right? And the function signature that we're interested in encoding here, which we have to put in string, is pawn, right? And that should be everything that we need. I will drop this. In the chat in a moment if I'm correct and this is successful. So this should send a transaction from my address to my delegation contract address and trigger the fallback function with very specific data that is going to trigger the pawn function in delegates, which will change the owner in the context of delegation. So that's the chain of events which should happen now. If it does, then I will drop that last little bit, this web3.eth.avi.encode function signature in. And let me see if I await my contracts.owner. Woo! There it is, right? So delegation has happened. Contracts have freely mutated each other's storage. Chains of events have been kicked off. We're navigating our way through the infinite. We understand a little bit more about smart contract storage, or less. Yeah, it's also a possibility. I sometimes feel like that. The more I learn, the less I know. I cannot get the chat to pop up, so let me just that's the last little piece that you'll need in your transaction if you're following along. Yeah, and this is delegation, right? The thing that extends this, I'm going to hop one tutorial forward into Vault because, like, again, it helps us examine some of the deeper aspects of storage and how this stuff is actually working. Because as I say, you know, I mean, like, whew, it's a lot to take in, that there are these different kinds of storage, that which is associated with the contract and permanently stored on chain, and then some of what Sylvia and I have been mentioning in terms of memory and call data. So the reason that we have these different kinds of storage available is that it's very, very expensive to store any kind of data on Ethereum. In fact, the cost for an S store, I think, is 20,000 gas, and the cost to update it is 5,000. So if you look at some of the calculations here, and I think that's in the is there a theoretical limits, you'll see both Vitalik's answer that you can kind of have 2 to the 261 bytes stored in a contract, but somebody went and actually calculated the cost of that, which is a lot, right? Even at the price of Ethereum at that time was significantly lower than it is today. And you'll see, like, the amount of storage that 2 to the 261 bytes actually corresponds to in terabytes, and the amount of ETH that it would take to sort of like do that sort of thing. So it's very, very expensive to store data, even though you have this potentially infinite array, this key value mapping in each contract, which has 2 to the 256 keys, each key capable of storing 2 to the 256 bits, yeah, or 32 bytes with each key. And the way that we kind of navigate the expense of storing stuff permanently on chain is by having memory and call data. And these two things are really useful for executing stuff that doesn't necessarily need to be etched in stone for eternity. There's some really funny stuff around here about, like, do you really need all of this data in your contract for eternity? Which is kind of interesting to think about given what we've been speaking in terms of time. But it's worth also understanding just a little bit more about like memory itself, because memory is split into call data, which, as I just said to Sylvia, like that's mostly call data is the function parameters. They're kept in memory for the duration of the execution of a function and then discarded once the function is executed. And stack is really like potentially even cheaper than call data, but it's mostly just used by the compiler. And like if you go and start debugging your contracts and stepping through the opcodes, that's when you'll see what is going on with the stack, in particular by following that video from Will It Scale number 8 in the playlist. Will give you a much better understanding of the stack. And the reason that that's interesting is because the EVM is a stack-based virtual machine, which is not the only choice for virtual machines, right? We can have stack-based machines, we can have register-based machines. And there was a lot of debates in the early days when Ethereum was being designed before the Olympus testnet of whether it would be stack-based or register-based. And in fact, Vitalik himself had tended toward the register-based approach because it seemed sort of more elegant to him. And it was really a man called Andrew Miller, who has been very heavily involved with Zcash and the Electric Coin company more than Ethereum in its later days, who suggested that he use a stack-based approach for various different reasons. This is the prehistory post that I'm talking about, and here you can see Andrew and Vitalik discussing this particular architectural choice. Stack-based machines are easier to optimize, and they do require a few more opcodes, but because of the way that like register-based machines allocate memory, there's some like subtleties around there, which, to be honest, I don't fully understand, but it turned out that like a stack-based approach was probably just the better thing to do. And that's why you have these stack variables. Then on top of the stack, you have like memory, which is stuff that is executed in the context of a particular function and then discarded. And then like you have storage, which is what is used permanently and what we're looking at when we speak about these slots, which is like stuff that is stored forever in all of the different slots. And the slots speak to this kind of like stack-based architecture and how the data is really handled at a deep level in Ethereum. And it's what you need to be aware of when you're declaring sort of state mutability functions like public, private, these sorts of things, right? Because like one of the misleading aspects of the private state mutability declaration is that these things aren't really private. Right? When I declare something as public, that means that like there is an automatic get function that is written for it at compile time. So anybody can simply call, like contract.owner and have that returned to them immediately, no problem, right? Writing private means that like you're not gonna, it's just gonna give you an error. It's not gonna return me the password, which is really great in the context of this vault. But just because it's private doesn't mean that I can't access it. If I understand this stuff about storage and how these slots work, you'll see that like the object of this particular tutorial is to unlock the vaults. And in order to do that, we have to pass the correct password to it, and then off we go. But what the hell is the password, right? And as I was just saying, if we get a new instance, because it's declared as private in scope, it's not as easy as simply calling contract.password. It's not going to give me what I want. But when I understand that the storage of each contract is organized according to these slots, I can do some sneaky little things, So like if I, for instance, here call awaits contract dot locked, for instance, right? Because it's public, it returns exactly what I expect, true, right? Like, and we've deployed our own new instance. It's constructed with the locked variable set to true, and locked is a public Boolean, so I can immediately get it, no problem. But if I await contract password, first of all, you can already see, right? I can do that, but oopsie, it's not a function, right? Because I've declared it as private. At compile time, there's no get function written for it, and so it's private. But of course it's not, because all of this stuff exists on a public, accessible adversarial network. And while I can't automatically get it, I can look into the contract storage and find it, right? And I know, moreover, by looking at the way that this contract is structured, that the password is going to be at slot 1, right? Locked is what's stored in slot 0. And then at slot 1, we have this bytes 32, which means it takes up a whole slot, which is really convenience from the Ethernaut team. And that's where the password is going to be. So I just have to examine the storage at slot 1 of this contract, and I will have the password. So this is just meant to demonstrate that, like, even if you declare your variables as private, they're not really private, right? They are accessible in that contract storage. And there is a public RPC method called eth get storage at. So if I have your contract address and I know which slot to look for, thank you very much. I can crack your vaults. So this is really, we just took a look in our send transaction to delegation at our web3.eth methods. And here, as I say, we're going to try and get, not the accounts or the balance, we want to get the storage, right? So there it is, get storage at. And in order to satisfy the parameters for this particular function in our library, we need to pass it an address, i.e. this is the contract where we want to get the storage at. And we need to pass it a slot. And we know that it's going to be slot 1 because it's indexed to 0. So locked is at 0, password is at slot 1. And there we go, right? Whew, there's our password. So it's literally as easy as that. And you need to be careful of these kinds of things. Don't assume that just because you've declared something to be private, that no one can see it. It just means that there's no get function conveniently written for it. But if people know how to examine your storage, it will be there in plain sight for everybody to see. It's for Sylvia and others, it's convenient that this is declared as a bytes 32, which is the same as like 256 bits, because it means that it takes up a whole slot. Sometimes when people, especially like advanced developers, are writing like really good Solidity, you'll see that they'll declare their variables in very, very specific orders and ways, so that you can have like many uint8s stored in one slot, right? That like if you have something less than 256 bits, the EVM will like shove them all into the same slots until it can't fit anything more in there, and then it'll move on to the next one. The exception for that, it's not really an exception, just as it's defined in the yellow paper, is that arrays, mappings, and complex mappings always have their own slots. And that's just because of the way that they work, which is also like interesting to know about and endlessly frustrating if you're trying to write things like dynamic arrays. But that's a feature of the stack-based 256-bit architecture that we're beginning to examine and look at. Anyway, we have our password, which is hilarious, because we knew which slot in storage to get it. So if I just copy that, and all I'll need to do now is call this unlock function with the password, and it'll set lock to false, and I should be able to submit my instance. So if I await the contracts.unlock function, and send it all at once. That should pop up a transaction for me, and I should be able to crack it. Let's see. seems like we've been successful. There's some receipts, which has a status of true, so that's kind of exciting. We can check by again asking for our locked public function. It's false. Wonderful, wonderful. So we've definitely passed this level, and we just need to submit our instance to prove that we have indeed unlocked the vault, and that we understand that even when we declare things as private, they're not really all that private as a result of the medium in which we're working, which I think is wonderful personally, but it is something that you need to consider when you're writing contracts. And there we have our rainbow splurge through the console. Everybody's delighted. Life is good. Labradors are gamboling through fields of daisies. You'll see here that one of the recommendations that they give is if you want to ensure that data is private, then you need to encrypt it before you put it on chain. And that one of the most promising ways for doing this kind of thing is ZK SNARKs, which stand for succinct non-interactive arguments of knowledge, meaning that we can have some piece of data which we can prove does indeed satisfy some condition without saying what the condition is or how we got there. It's wonderful. It really is moon maths, as it's often described. There are some really incredible people working on these kinds of things. Andrew Miller is one of them, in fact, the man who is responsible for Ethereum having a stack-based architecture. And if you are interested in this kind of thing, Elena Geralt from the Electric Coin Company is in our Slack and hosted a Junto in the first week on zero knowledge stuff. So if you bug her, I'm sure she could be encouraged to do another one. And if you do, and you're interested in this kind of thing, definitely ask her about Halo, which is self-recursive zero knowledge proofs, which are truly mind-boggling. And if you're a fan of this kind of thing, then Halo is next level. It's really incredible. We have a little bit more time, so I am going to also do this force tutorial because it demonstrates, as I sort of skated a little bit over how that parity wallet hack actually happened, which is the delegate call functionality to some libraries wasn't properly instantiated, but then what is this thing about self-destruct that somebody called and then posted in their GitHub repo? Oops, I killed it. One of the most classic GitHub comments of all time. And we're gonna have a look at that particular feature of Solidity and the EVM, because now that we've sort of understood that there are these global variables like block number, block hash, all of these kinds of things, and that it's not really good to write logic which relies solely on that because other people can replicate it and calculate before you what you're going to calculate and therefore manipulate your code. We've understood that there are things like tx.origin and message.sender, and that these can differ when you call your own contracts, and that it's not good to write in a particular token transfer logic or these kinds of things, which is not aware of the ability to have different tx.origins and message.senders. We've looked also at delegate call and how to pass the same context along any chain of calls that we have and to freely mutate contract storage. And we've now understood more about hey, storage works in slots. There are many of these different slots, each of which can store a whole bunch of stuff, potentially on into infinity, but we would likely hit some kind of hash collision or... Glory, could you maybe mute? Thank you very much.
What's the point? To demonstrate skills. Your brother will be good at this.
Glory.
Here. Let me show you. Just is a performance. You must show skill.
1 moment.
feel and no one.
Where is the... Thank you very much. Sorry about that. Back to here. Yes, so we've understood all of these things about how storage actually works. The fact that you could potentially store nearly infinite amounts of data in any smart contract, but that's limited by both the cost and other inconvenient things like the heat death of the universe, as well as hash collisions, which are more and more likely after 2 to the 160, I think, which is around like the, like you can have as many addresses as, again, like sort of 2 to the 256, but like around 2 to the 160 seems to be where like hash collisions become more probable. There are statisticians and other sort of cryptographers and mathematicians in the Ethereum stack exchange who are more exact about that than I am, but that's kind of just an interesting little piece of information. And understanding all of the stuff about not only how storage works, but all of the global variables that are accessible in Solidity, we're now going to look at one final one, which sort of completes the loop on the parity wallet hack, not just in terms of delegate call, but self-destruct, which, when we were more nihilistic existential goths back in the beginning of Ethereum, was called suicide. But happily, we've kind of moved past that particular, sort of highly hormonal teenager phase, most of us anyway, and we're now more professional, so we call this particular function self-destruct rather than suicide, and it's what we're going to use to attack this particular contract. The description here says some contracts will simply not take your money, so the goal of this level is to make the balance of the contract greater than 0. Here you can see we've got a contract with absolutely nothing in it except a cat, which is wonderful because cats actually rule the internet. That's also a whole other rabbit hole, or whatever you would like, for another day. But we need somehow, this contract implements nothing, right? There's no logic in the fallback, there's no functions, there's nothing. How on earth are we going to get this contract to accept Ether? There's no payable function in it, there's nothing. So like at first glance, all we're sort of looking at is a cat and being like, well, what now? But as I've kind of hinted at, there is one way that we can force this function to accept ETH, which is by recourse to this low-level Solidity call called self-destruct. This again is going to require that we write our own contract. So as per usual, let's get a new instance because we will need to reference it. Get that on Rinkeby, which is very exciting. And I'll see. It takes a little moment. There's my instance address. Wonderful. I'll come back for that in a moment. And we're going to come back into Remix and our directory, top left of the workspace. And we're going to create a new contract following the same convention that we've been using. So we'll call this one attack force.sol. Let's begin with our SVDX license identifier. We'll use MIT again. We can declare our pragma. Solidity, let's say 0.8.0. And we're not, there's no functions or anything in this contract. There's literally just a cat. So we're not going to write any interface or any of this kind of stuff like we've been doing. We're just going to write a simple contract that self-destructs. So we can write our contract called attack force, which sounds amazing. I'm very open to calling this attack space force if you would like. I'm going full orange head politician on you, but maybe another time. I'm just going to comment here that what we have to do is we need to seed this with ether, right? Because we're going to need to get some balance associated with this contract. How self-destruct works is that it takes the balance associated with any given contract and it transfers it to another address, and it sets to 0 all of the storage associated with this address. So if we create this contract with a little bit of ether in it, and then have a function that calls self-destruct and specifies the address that it self-destructs to, then it will take whatever balance is associated with this contract and transfer it to the address that we specify. So our constructor, we don't need any parameters, we just need to make sure that it's payable. And there's that. And then we can have one function here, which again, we've been using this wonderful hacker language called pawn. We need to also specify the states, the state mutability, which is public here. And there is this low-level self-destruct call. And the low-level self-destruct call, as I say, expects us to pass some address to it. And it will just automatically move the entire balance associated with this contract to that address. Now, interestingly, let's also just make sure that this is public. Interestingly, the way that this has been implemented, if you come to your compilation tab, second one down in the very left-hand panel of Remix, and try to compile this at 0.8, you might run into some issues. And I wasn't entirely sure why this was the case, because they've changed even more the way in which self-destruct is implemented at the low level, precisely because of this kind of problem. And what had happened was like a few hacks have occurred because people wrote contracts whose logic depended on that contract never having ether. And then they were very careful, and they made sure that none of the functions were payable, that the fallback wouldn't accept ether, all of this kind of stuff, and then assumed that they could rely on the balance of that contract being forever 0 in some critical logic, which you can't do, because anybody can send you ether via the self-destruct, and it comes directly to your address as a result of the way that this low-level functionality works. And that's problematic if your logic relies on your contracts having no balance. You can see that, again, because I've changed compiler versions to 0.8, it's taking a little while, and I'm not expecting this to compile correctly. And yeah, you can see that there's some problems with both the visibility on our constructor and the mutation right here, like invalid implicit conversion from address to address payable there, which is kind of a little bit annoying, but we should be able to get past it by using an earlier compiler version. 0.6.0 should allow me to compile this. If I go back to, there we go, right? And that's something else that I just wanted to highlight, a subtle little point in this particular guild session, is that just because the latest version of the Solidity compiler doesn't let you do certain things which we have discovered in time to be potentially malicious, doesn't mean that you can write code that assumes everybody is using the latest version of the Solidity compiler. Right? I can just write a contract that goes back to some previous version of the compiler and still potentially get it to compile and put it onto the network. And if your contract relies, for instance, on this thing of having no balance or other little low-level things, it's still potentially vulnerable. And so we've got our compilation done, and we can come make sure that's in our deploy and run transactions tab. It's injected web3. It's the address that I want, which is 0x5f. That's the one that I want. And I want to deploy this with some ether. So like you can see that you can always like send a transaction with some kind of value. I want to deploy this contract with a little bit of ether so that when it's self-destructed, that little bit of ether is sent to the contract that I'm trying to get a balance associated with in Ethernauts. So I can just use Gwei. I don't know. 100 Gwei should be enough. That should be everything that I need. I think if I deploy this onto Rinkeby, I'm not 100% sure that 100 Gwei. I think it'll be good enough. Let's check this. So we've got it deployed. If you come down to your deployed transactions, your deployed contracts, you should see there's my attack force below attack telephone from earlier. And if I call pawn, this should trigger the self-destruct function and send whatever balance is associated with this contract to a force Ethernaut contract. I wonder if it's going to be enough. I sometimes get a little bit, like one way is 10 to the minus 18 ETH, and so sometimes it doesn't quite get picked up. And I remember that there was a subtlety around this when I was testing it a few days ago. So let me see if I await my contract. Can I do this? Balance. I just don't want the player. I want the instance. See. Okay, we should be good. There we go. We can see that my instance now has a balance associated with it, even though there's literally no code in it. It's just a cat. Still, I love this is one of my favorite levels just because of this cat. Just sat here, chatted with him for a while when I was going through these levels because I'm a weirdo. But because we do have a balance for this instance, we should be able to submit it and hopefully pass. Let's see. Hold thumbs here. Some moments of real truth. And whenever there are such moments, then inevitably mining transactions takes a little bit longer because there are, actually, despite everything that I've said, really, Ethereum is just run by cats. As you can see, this face here in the rainbow is actually a cat because they're everywhere. And we have indeed managed to pass force. So we're 9 tutorials in. We've conquered everything from Hello Ethernauts to the Vault. Hopefully we understand a little bit more about these global variables, about how storage works, about what an injected Web3 provider is, how MetaMask works, what a remote procedure call is, how to program and code from our console without needing any fancy software, how to use an integrated development environment, what Remix is about, all of the different things that you can do there, including writing your own smart contracts, deploying them onto any network that you like, compiling them, testing them, learning about ETH, which is probably just the last recommendation that I will show you. If you are really into this, you'll see that there are a whole bunch of featured plugins on the homepage. Learn ETH, amazing stuff. You'll have like the basics of this IDE, an introduction to Solidity, the basic use of these JavaScript libraries. If you learn about Web3, you'll know about ethers. There's then some really wonderful stuff about proxy contracts and libraries, which are incredible and really important if you're going to be writing this kind of code, potentially for production. And then the one that I'm doing at the moment, which is opcodes in the debugger, because debugging your smart contracts has traditionally been very, very difficult. It's not as bad these days, but learning about these low-level architectural decisions of having a stack-based VM and what that means in terms of pushing data on and pulling it off and when it happens and how the code jumps around and what the difference between stack variables, call data, memory, and storage are all really wonderfully revealing. And they can be very useful in terms of, again, like developing your own intuition about what it means to write a language of defense, to write in a way which is robust and resilient and which defends your ideals by thinking like an adversary, right? So that, like, one of the big points that I'm kind of constantly making when it comes to these smart contracts, right, is that, like, any kind of revolution in history has really been let down because the humans on whom it depends are inevitably corruptible. This is not a bad thing. It's wonderful to be human and to be flexible, open to change. There is a lot of really beautiful and necessary aspects in our ambiguity. But what is really interesting is that when I write a smart contract, I can encode into it some ideal, egalite, liberté, fraternité, and those ideals live on independently of me, particularly if I've been adversarial in the way that I've approached writing it. And so, for instance, like some curatorial algorithm that I wrote now lives on Ethereum permanently without any interference from me. And the ideals that are encoded into it, that there's no owner, that there's no middleman, that no one receives any kind of fee, that there is just direct flows of value from the people who rank highly to the people who are actually seeing their content and back when those people who are seeing the content vote on it. That really simple economic ideal does not depend on me any longer. It doesn't depend on what I say. It doesn't depend on my interpretation. It doesn't depend on me becoming jaded and cynical about the way that people use these kinds of tools to farm greater yields without concern for the impacts on their wider environment and the other people. None of that matters when we learn how to develop this kind of intuition about, you know, what we've been calling the language of defense. So incredibly, for the first time ever in this guild, we have ended a little bit early, which is really wonderful because it should give you a little bit of time to kind of sit back and relax before Kia's DAO session, which promises to be really, really good. And she is genuinely an incredible person who I can't say enough good words about. We have another few minutes for questions before that. If you have any similarly speaking comments, jokes, songs, dances, all of these are welcome if there are no questions.
I mean, if nobody has questions, I want to ask about cats and the internet.
Oh my God. Incredible. Man, that's funny. There's some wonderful like Reddit and other kinds of rabbit holes that you can go down, which have to do with this, that the internet looks like a cat. If you collect if you scrape as many images as you can off as many different sites as you can, the vast majority of them have to do with cats. It seems that there is this particular kind of really interesting cultural feature or artifact of many of the people who have like been online longest, that they are cat lovers. And it kind of checks out, right? Like the people that have been using the internet longest tend to be like a little bit more introverted. They tend to spend a little bit more time kind of indoors or in front of their like machines, which also, like, I don't know, has something to do with a proclivity for cats more than dogs. there's some really, I don't know, there's like, I think like an academic research paper once wrote this because somebody was looking at like, I'm not sure if they were generative adversarial networks, but some kind of like early neural net processing on like a wealth of images that they'd scraped from across the internet, and it like came out as a cat, which, you know, kind of plays into this, I don't know if it was The Simpsons or some other kind of one of the popular cartoons speaking about like how cats really control not just the internet, but the world. They're just not letting on about it. And being sort of wonderfully mysterious. Yeah, there's some links maybe that I can dig up for you. It was the rabbit hole I fell down a few years ago, so I'm not as fresh about it as I used to be. But it is a very interesting symbolic animal as well, if you're interested in the archetypal significance of these kinds of things.
Yes.
One of the more interesting places to go and look at this kind of stuff is ancient Egypt, and there's some symbology of cats around that. It's very interesting because the pharaohs were often depicted as riding a chariot with a horse, I mean, with a pig and a dog, which was symbolic of being able to curb the two competing tendencies in human nature. The pig, that which is attracted, the pig is attracted to everything. It literally vacuums up whatever is in its environment. Strong attraction to everything. The dog is repulsion, right? It barks and repels everything. So once you've curbed the competing seeming opposites of attraction and repulsion in your own self, you have this god king like figure, which is what the pharaohs were supposedly all about. But they I won't go further into that. Perhaps it's significant just to say that, you know, like there are some wonderful stories about where that ended up for them, because they lacked some of the perhaps wisdom and humility that comes further along from curbing those two impulses. And I think that a lot of that was caught up in this interest that they had in cats. The sort of like regal nature of the cat as being like incredibly like noble in some sense, right? That the cat in many different traditions from around the world is significant of the ability to be like at once somewhat detached and aloof from, in this really cool way, of like the events happening in the world, but yet like intensely focused as well. So I know in like Sufism, for instance, like one of the like greatest Sufi teachers of all time said that he learned from a cat, right? That the cat could remain absolutely still for hours on end without even moving a hair, let alone breathing, watching a mouse's hole. And that muraqaba, that particular kind of awareness and meditation, was what he had learned from watching a cat for days on end. So there's this really interesting symbolic significance of both the neutrality which cats are so often associated with, and yet that intensity of focus and skill and precision, which is kind of associated with them too. We talk about cats forever.
Yeah, amazing.
So, but you were the one who did the analysis of memes, you know. So I think that you should look further into this and see with what prevalence cat images occur according to the fluctuating prices of magic internet money. See if there's any correlation there. Tell us. Yeah, we'll keep an eye on the appearance of new kinds of cats, and then we'll know what's going to happen.
Yeah, so for the rest of you, the original inspiration for that research was a paper called On the Origin of Memes, which was similar to Darwin's paper on the origin of species. So yeah, memes behave very similarly to genes in the biological world. So memes are the genes of the internet and society. That's what Richard Dawkins and other people suggested. So yeah, that's what Andy is referring to. And yeah, cats do rule the meme world. Cats and frogs.
Yes, indeed. Okay, anything from anyone else? Or take 10 minutes to get some tea, stretch a bit, and then come back for the DAO session if that's something that interests you, or just go and hang out with your cat and enjoy life.